Welcome everyone. My name is Kilo Konoma and this is
Mads.
Today we're going to talk about the algorithm we've been working on for a very long time. So this is a very interesting thing for both Mads and I. What we sought to clarify was the field health. And today we're going to first start with the problem and the definition and some data set. Then we're going to go on to the implementations and some insights, any problems we encountered. And then we're going to end with some results and conclusion.
Okay, so problem definitions. So originally me and Caleb wanted to speak something about health and kind of see how AI could be helped to solve this. So we looked around and found these statistics that 3% of fetal babies are born with birth defects, and also that the birth defects are accountable for 20% of the total infant death as well.
So basically, our goal was to program this 5 algorithms. Oh, sorry. Wait, go back. And we're thinking, well, we just chose them randomly, but also because of the unique nature of all of them, we chose 3 unsupervised, 2 supervised, just to see, kind of like compare them later on. And yes, we chose to do all of this in C# because everyone else did it in Python, and we wanted to be a little bit cool. So let's do it a little harder because it's easy stuff, right? So we went with C# and yes.
So our dataset we chose is from Kaggle, and our dataset basically contains CTG data, which is observations extracted from cardiogram exams. And this dataset, you can basically use it to identify and classify the health of fetuses and put them into 3 classes, which is normal, suspect, and pathological.
All right, now.
Yes, sir. The approach. So once we had our dataset in place, our next key was to find the key features from this dataset that we actually wanted to use. So to achieve this, we employed a correlation matrix, and then we identified 4 attributes with the strongest absolute correlation values with the fetal health variable, which is the one that is used for classification, the one that puts them into the normal, suspect, and pathological one. And when we selected these, we moved on to data partitioning, which involved doing the common practice of data partitioning and did the common practice of splitting the data set into 80% the training data and 20% for the test data.
Yes, and when we did this, we needed to do something called stratified sampling because the data was imbalanced. So we had more of class 1 that we had than class 2 and 3, which we're going to come into later on. So stratified sampling basically did is that when we had the data, we made sure that we had 80% of class 1, 80% of class 2, and 80% of class 3. So it wasn't, imbalanced. All right, so these were the features that we worked with. I don't remember how many there were, but there were many. And the values here, they were continuous values, except from the classification, which was the fetal health, which was basically 1, 2, and 3. Now, after doing this correlation matrix, we got these 4 features, which were the key features, the most strongest correlation. So going on during our algorithms, we actually worked on using these features, but we compared them with using all, which we're also going to come into later on. K-means, yes. So for the K-means, we have, this is what we're going to show you guys a little bit more of. And yes, you can also see what I was talking about, that in class 1, we had more samples here than we had in 2 and 3. And the different classifications were normal, suspect, or pathological.
So K-means was one of the algorithms we implemented, and it's basically an unsupervised machine learning algorithm used for grouping data points into clusters just based on the similarity. And essentially what it does is that we start with K amount of clusters that you can choose yourself, and then you assign data points to the nearest centroids, and then update the centroids based on the distance from these data points that it gets assigned to. So here you can see that they've been initialized in these positions, and then they will converge. Yes. And then find a center from the data points that they've been assigned to. And this will then continue until convergence, which means it will continue moving until the distance that has changed is not significant enough on a set variable that we chose.
Exactly.
So
we had a limit.
Yeah, exactly. Yeah. So one of the problems we had was actually one that Magnus covered in one of his lectures, which was when the centroids gets placed too far away from data points.
Yes.
But in our case, it was instead that one centroid was closer to all the data points than all the others, which made it get assigned to all the data points in this picture right here, which would then lead to class 1 getting 100% accuracy and the other ones getting 0%.
Yeah, and we fixed this by normalizing we normalized basically the centroids. So we normalized them, so they were basically here. Or we normalized the feature values, and then it fixes itself.
We introduced also a min-max bound, so we knew that it gets initialized within like proximity of the data point, so it doesn't end up being too far away. And if it in the first step a centroid didn't get assigned to data points, it would be reinitialized with a new position.
Yeah, exactly. That's what we did as first. Yeah. All right.
So this is the k-means results, and as you can see here, the K166 has the overall highest accuracy, right here of 88.5. But we also wanted to make note of K34 because it's actually a way lower number, but actually manages to perform really well as well.
Yeah, and it depends on obviously what you want. If you want accuracy, I think you go with this, but maybe you want speed and efficiency, then it's as good as going with this or maybe even this one. All right, on to the KNN. So for the KNN, we started by creating a flow chart just to understand how it works. And for our KNN, we use the So for our KNN, we use the Euclidean distance to measure the distance. I know a lot of us have talked about the KNN already, but what I could say here is, let's see. Basically, KNN works in a way that it checks for a sample and it checks the nearest samples in the training space. And depending on what value k, that means how many samples are closer to that test sample, we know what class it's around. So this is how it works. So we have the test sample, which is this black spots, all right? And let's say we have a k value of 3 in this case. It checks the 3 closest. And in this case, it will look something like this. Yes, it will look something like this. So this one became the purple color and etc. The results for this KNN, we can see here. So this one shows the result when we're testing all of the features. And yeah, we got 90%, all right? But then when we tested the key features, guess what k value we had?
3.
That gave the highest accuracy.
1.
You think 3? You say 1?
Yeah.
You're correct. 1 actually gave us the highest accuracy. Isn't this crazy? I mean, it kind of shows that this key value or key features we selected, they were really strong. So 1 gave the highest accuracy, and that was that for our results for the KNN.
So outlier detection, most of you already know, but it's basically about identifying the points that deviate from like the average. And basically when we wanted to do it, we didn't know how to actually tackle the problem. So we normalized the data, and then from that we calculated the average class points for each. And then we were able to set a cutoff range. So basically we could detect like what values were on the outer 20% or 10% or 5%, depending on what we wanted to look at. And that's basically what you can see here. So here we have like the average sample for the fetal health variable 1, and then we have like an outlier here, and you can clearly see that the values are much higher and kind of deviate from the average, which is why, for example, this one was marked as an outlier.
Yeah, and the reason to why our results looks like this, not as visually intriguing, is because we did all of this in C#. So working with graphs isn't as easy as in Python and so on. All right, onto the random forest. So random forest consists of decision trees, many decision trees. But before they enter this decision tree, they have to be bootstrap sample, which means basically dividing. So we have samples for this decision tree, samples for this one and that one. But when bootstrap sampling, what happens is you can have the exact same sample appearing more than once in the same decision tree. All right. So this was our flow chart, and going through this quickly, I can tell you that we didn't use, as Almar talked about, using the
entropy and
entropy. Yeah. So we use Gini impurity,
yeah.
which in this case you want this value to be as, let's see, I think you want it to be as big as possible. I think I actually forgot, but something like that. It should be as big as possible. I think the other one is as low as possible. Yes.
Information gain should be max, but maybe impurity should be low.
Yeah, the other way, the other way around. I forgot that,
Yeah.
but yeah, I think it's the other way around. But either way, so what we do is that we have different thresholds. So we test, and then we split the data. Yeah, it's a long process, right? And then we just check for the best Gini impurity index, and then we choose that threshold. And also for evaluating, this is where the different decision trees come into play. So we've saved them into something called, we had like a knowledge base. So it was saved in like a JSON format. So we read all of that data, and then we just put them into the different decision trees, get the classification type, and then majority carries the vote.
The random forest results, so basically what we did was we wanted to see how the different variables would change the performance of the model. So what we looked at was min sample size per leaf, which is like the least amount of data points that were allowed per leaf until it had to stop, so it didn't continue on further and overfitted. And we had the maximum tree depth, which is just like the layer or how many times kind of goes down. And we had the bootstrap sample size, which just refers to the numbers of samples drawn when actually creating each decision tree. And the one that gave the best accuracy was the bootstrap sampling 5, which gave us an overall accuracy of 90.4 out of 14.
Yes, and what we did is that we started with this, there, and then there. So we took the best accuracy, the mean sample size. We took it from the one that had the best accuracy here, then we took the max tree depth from the one that had the best accuracy here, and then we had this. Oh, shit. Okay. All right. On to the feed 4 neural network, the artificial neural network. So what should we actually say? This is the flow chart. We have something called for the forward propagation and backwards propagation. For our activation function, we used softmax. We tried sigmoid, but it wasn't as good, so we just switched it up. Basically, in neural network, we created this graph because it was quite a complex thing to do in C#. So you really needed to understand in depth what's going on. So we have these are the weights, all right? These are the weights, and then the biases are on each neuron. We had this amount of features when we're testing our neural network, and we had 3 output because we had normal, suspect, and pathological. But this was just for
To showcase.
yeah, for the showcase, exactly. Either way, so when implementing this, now this gets complex. So I needed to draw all of this out to really understand what is going on, to be able to code it, right? It gets complex, but I'm not going to go deep into it. But what I can say is, when calculating the hidden layers, the output or input of the hidden layers, we have to make sure we have the weights, we add with the sum, we have the linear transformation, and then we turn it into a sigmoid function, and then we have the hidden layer, all right? And we did kind of similar thing to get the output layers. You can see the colors, they match the colors of the output layer. And the propagation was the fun part, the most difficult part. In this part, I can say that one of the problems we had was, so this means you're multiplying pointwise, right? It's different from actually matrix multiplication. So when we missed this, the calculation, so the algorithm didn't really perform as we wanted it to. But either way, we continued this all the whole way down to update all of the weights, all of the biases, just to really understand what's actually going on, to be able to implement it, right? And this was our result. Now, we weren't happy with the result. We looked into this several times. We tried different learning rates. We tried how many neurons in the hidden layer. You can see that here, it didn't really perform that well when we were switching that off. But here it performed good, here it performed really bad. And you can see the learning rate there. And then we also tried out some other hyperparameter, which was the batch size. And well, we got at highest like 77%, but it was classified one of the classes really high and the other ones really low. So our argument to this is, we don't think that this FNN was sophisticated enough to be able to understand the intricacies. I don't even know how to say it. But either way, yeah, it wasn't complex enough to understand what is going on in the data. And perhaps maybe it was being overfitted. We tried so many times, I don't think you understand how many times. But yeah, so this was what we had. It's not even going next.
So conclusion. To conclude, we can say that the best accuracy for us was the KNN algorithm when k was equal to 1. But as you can see, also the model keeps an overall high accuracy throughout like all the different k values, so it performed well.
Yeah.
And the reasons for this we thought could be because of the data set that we got from Kaggle was already well defined and really good, and had like clear separation points since it could like be enough with k equals 1. It could also be due to our feature selection. Perhaps it would have been different if other features were selected, or if we performed algorithms on all the features as we did. As we can see here, as Kenneth spoke about before, so instead of k value being 1 as the best, it was like more on the range of 4 until 8, with 7 being the highest accuracy. Yeah. And also, yeah, it would have been funnier if the FNN performed better to see if it could like kind of compete with the accuracy of the KNN, but yeah, as we can see, it is what it is.
All right, you're all welcome.
Thank you.